Today I will talk about this topic called decision trees. I'm sure people who have been in data science for quite some time now will be familiar with this topic. But even from a non-data science perspective, this is a good to know sort of stuff because this can be used not just in machine learning, but even to take any kind of decision. This is sort of a mathematical way or an algorithmic way of doing it. So this is what we call as a supervised learning technique. So you remember a few weeks back when we were talking about one other data science technique, we were talking about two types of techniques. One is called as supervised and the other is called as an unsupervised learning. So a decision tree is a form of supervised learning because in the data set that we use, the value of the target variable will already be present, and you will be training this model on using the already present labels or the target values. That is why it's called as supervised learning. And this is used for both classification as well as regression. Classification as in taking a binary sort of a decision, a yes or no decision or win or lose decision, that sort of a decision. Regression as in a continuous variable prediction. So what would be the sales or what would be the temperature, that sort of values. So this can be used for both classification as well as regression. And the principle is what we call as a top-down approach, or more technically, this is called as a recursive binary splitting. Okay, what this actually means is if we start from the top, we make two splits and then we repeat that process again. So this is the same process of starting from the top and making two splits in each level of the decision tree is repeated successively, and that is why this is called as recursive binary splitting, because we make those two branches or two splits, right? So a very simple and a crude example. So let's say we have to determine whether a person is fit or unfit. Okay, fit as in physical fitness. So let's say you have a data point called as age. Okay, that is the age of the person. If that age is less than 30, then the next thing that you ask the person is whether he eats pizza. Okay, so normally people say that pizza is an unhealthy food, right? So if the person says it's less than 30, and if the person is in the habit of eating pizza, then they say that the person is unfit. Okay. On the other hand, if the person says it's less than 30 and he doesn't eat pizza, then they're saying that that person is fit. Okay, so this is a very simple decision. So eating pizza is one of the parameters or one of the criteria for making the decision of whether a person is fit or unfit. Let's take there is another parameter, exercise. So if that person says it's less than 30 and if he exercises, then he is fit. If the person says greater than 30, greater than or equal to 30, and if he exercises, then he is fit. And if he doesn't exercise, then it means he is unfit. So this is another parameter for taking the decision of whether the person whether the person is fit or not. Okay. So this is a very crude example, rough example, just to help you understand that concept of decision tree. In reality, when you are talking about it from machine learning context, there will be several other variables and the data set will be huge. So like this, you will be able to see many branches of this decision tree because of many variables and the large size of the data. Okay, but this is what it basically is. Certain terminology related to this decision tree. So this particular starting point of the decision tree is what we call as the root node. Okay, and then each of the subsequent decision points or the decision parameter, we call them as decision nodes. So this eating pizza or not, whether the person is doing exercise or not. So these are what we call as decision nodes. And the point where the tree terminates, so the point where you declare whether a person is unfit or fit, so that is what is called as the terminal node. So terminal as in basically that word is used to denote the end of something, right? So beyond that point there are no other further branches of the tree, so we call this as the terminal node. And any particular section, so this entire thing is called as a decision tree. this particular section of one decision node and two terminal nodes. So this particular portion with these nodes is called as a branch or subtree, what you see over here. Okay, so this is the basic thing about decision trees. I will proceed to explain about how we actually build this tree, but any questions here so far? Okay, let me move on. So one of the primary aspects of building this decision tree is the choosing of the variable for each script. So for example, coming back here, in this point, what we do is we decide, we will determine whether a person is fit or not based on whether he eats pizza. Okay, in this point you're saying I will determine whether a person is fit or not based on whether he is doing exercise or not. But how did they decide on this pizza, and how did they decide on this exercise? And there could also be other factors such as blood pressure, sugar, or any other lifestyle behavior or whatever, right? So in reality, there will be so many other different criteria. Out of all those criteria, what is the best criteria that can be chosen? So that is what we mean here when we say choosing the variable for each script. Okay. So there are 4 methods to do this. The first one we call as Gini coefficient, and then there is a method called ChiSquare. Then there's a third method called information gain. The fourth method is called reduction in variance. Now these 3 methods that you see here, the Gini coefficient, chi-square, and information gain, these first 3 methods are used for classifying categorical variables, or used for building a decision tree with categorical variables, like we saw here, whether a person is fit or unfit, like or whether a team is going to win a match or lose a match, or whether it's going to rain today or not, or whether a person will be issued a housing loan or not. So for dealing with these sort of categorical target variables, we use the first 3, any of the first 3 techniques. The final technique, reduction in variance, is used for predicting the value of continuous variables. Okay, so for example, what is the temperature, what is the pressure, or what is the sales forecast given a set of input parameters. So for those continuous variables, we use this reduction in variance technique. So in today's session, I have not touched upon this reduction in variance, but just in case you feel you need more information, you can look it up. Today I'll explain how to calculate that, or how to build the decision tree using these 3 methods. Okay, so first method is Gini coefficient. I'm not sure whether you have come across this term of Gini coefficient. The Gini coefficient is not something that is specific to data science. So we use this Gini coefficient to calculate something called as income inequality. Okay. So you have these organizations like the United Nations, right? Where they publish several statistical tables. Okay, and one of those statistical tables is this inequality, income inequality index, and that income inequality is actually calculated using this Gini coefficient. Okay. Now I'll take a very, very simple example. In reality, how this Gini coefficient is used is income inequality between countries. So in each country like India, USA, UK, Japan, Australia, so for each country they calculate this inequality using this Gini coefficient. Now I will just explain a very, very simple example from a decision tree perspective. Okay. Now assume that there are 30 students in a school. Okay. Now out of these 30 students, 15 of them play cricket, which is half, 50%, right? Now out of the 30 students, we have 10 female students and 20 male students. Okay. Now out of the 10 female students, 2 of them play cricket, that is 20%. And out of the 20 male students, 13 of them play cricket, that is 65%. Okay. And then the other variable that we have, so like in this example, we said eating pizza is one variable and exercising is the other variable, right? So in this situation, the gender is one variable, and then the class in which the students are studying, so that is another variable. So let's say 14 students are in class 9, 16 students are in class 10. And out of these 14, 6 of them play cricket, and out of 16, 9 of them play cricket. Okay. So given this data, we need to identify, or we need to determine which is the right variable out of these two to achieve that split. So whether we should split based on gender, or whether we should split based on class. Okay. So this is the formula for Gini coefficient, that is p squared plus q squared. So p is what we call as the probability of success, q is what we call as the probability of failure, that is nothing but 1 minus p. So 1 is basically the 100%. Usually that's how we express probability, right, in terms of percentage. So that's the same thing. So if we are to split down, so for each variable you have to calculate this Gini coefficient, and we choose that variable for which the Gini coefficient is higher. Okay. So for this example, for the first step, we calculate the Gini coefficient for this gender split. Okay. So if we are to split by gender, then what is the value of P and what is the value of Q, right? So the female group has 2 students who play cricket, that is a 20% value of P and an 80% value of Q. Q is nothing but 1 minus P, right? So 1 minus 0.2 or 100% minus 20%. So that 80% will be Q and the 20% will be P. So P square plus Q square will be 0.2 the whole square plus 0.8 the whole square, which gives you 0.68. Okay. So similarly, for this particular node, subnode, the male subnode, again we calculate the Gini coefficient, that is p square plus q square. P is 0.65 and q is 0.35. So 0.65 square plus 0.35 square gives you 0.55. Okay. And then you calculate a weighted average of these two. So we have 2 subnodes, right? One for female and one for male. So for these 2 subnodes, we calculate the weighted average. So weighted average is what is the total number of what is the number of students in this subnode divided by the total number of students. So 10 by 30, right? For the female subnode. Similarly, for the male subnode, it is 20 by 30. So 10 by 30 multiplied by the Gini coefficient for the female subnode plus 20 by 30 multiplied by Gini coefficient for the male subnode. So you get a Gini coefficient of 0.59 if you are to split by gender. If you are to split by class, right, there are 2 classes, class 9 and class 10. Same procedure. So for the class 9 subnode, it will be 0.43 square plus 0.57 square. And then for the class 10 subnode, it will be 0.56 square plus 1 minus 0.56, that is 0.44 square, that is again 0.51. Same weighted average, 14 out of 30 are in class 9 plus 16 out of 30 are in class 10. Each of these weights you multiply by the corresponding Gini coefficients. So since both are the same, it doesn't make a difference. You get a weighted average of 0.51. And then what you do is you compare this 0.59 and the 0.51, and you determine that gender is the right variable on which to split the data because the Gini coefficient is higher for gender. Okay. So this is how you use the Gini coefficient metric to determine which is the right variable to achieve that split. Any questions here on this technique? Okay, let me move on to the next one. So the next technique to determine the right variable for the splitting is what we call as the ChiSquare technique. Okay, so for the ChiSquare technique, we use this formula: square root of actual minus expected the whole square divided by expected. I'll just show you what this means. Okay, so same nodes, right? So we can either split by gender or we can split by class. So gender has 2 groups, female and male, and class has 2 groups, 9th class and 10th class, right? And we have this basic data out of the all the females, how many play cricket, how many don't play cricket. Same thing for the males and so on. Okay. Now out of this or from this data, you calculate something called the expected values and the deviation. Okay. Now how do you calculate this expected value? So this is nothing but, just go back here for a moment. Now, out of the entire data set that you have, 50% of the students play cricket. Okay. So when you're saying expected value, then the same 50% will be applied on each of these subnodes. Okay. So if in the entire data set 50% of them or half of the students play cricket, then I will naturally assume that by default half of the females and half of the males will be playing cricket. So expected to play cricket will be half of 10, that is 5, that is 50% of 10, and expected to play cricket in the male subgroup will be half of 20, that is 10. Okay. And expected to not play cricket is again, so if 50% are playing cricket, then the remaining 50% are not playing, right? So 10 minus 5 are the remaining 50%. Same thing here. Okay. And then you calculate the deviation of this playing cricket category. That is nothing but actual minus expected. So actual is 2, and the 2 people actually, or 2 females play cricket, but expected to play cricket is 5. So 2 minus 5, that is minus 3 is the deviation. Similarly, for the male subgroup, it is 13 minus 10, actual minus expected, that is 3. And similarly, deviation for not playing cricket is same. Actual minus expected, but here we'll be considering not playing category. That's it. Okay. And then you calculate this chi-square value, which is using this formula: actual minus expected the whole square by expected. Okay. Now, actual minus expected is what we call as the deviation. So this chi-square also we calculate for both categories, playing cricket as well as not playing cricket. So this deviation minus 3 the whole square divided by expected, that is 5, and the square root of this entire thing. So my 9 by 5, and you take the square root, which gives you 1.34. Similarly for the other categories as well. Okay. Not playing cricket, and for same thing for the male subgroup. So 3 square divided by 10 and the square root of that value. Okay. So this is for the first classification, that is the gender split. If you have to split based on the class, again this basic data is what you already have from what we saw over here. How many play cricket in class 9, how many play cricket in class 10, and so on. Using this, you calculate the expected values. That is nothing but of the total number of students in class 9, half of them are expected to play cricket, that is 7. And here in class 10, this half of 16, which gives you 8, and remaining half that will be expected to not play cricket. And then the deviation, which is nothing but the actual minus expected, that is 6 minus 7 and 9 minus 8, which is what you see here. And the same actual minus expected whole square divided by the expected, and then taking the square root, same formula, which gives you 0.38. And then, so once you have these individual chi-square values, what you do is to calculate the total chi-square value for each variable, you just sum all these individual values up. So this 1.34 plus 1.34 plus 0.95 plus 0.95. So this 4.58 is the chi-square value for the gender split. 1.46, which is nothing but the sum of these 4 values, is the chi-square value for the class split. Okay. And again, you make that comparison. 4.58 is greater than 1.46. So since this chi-square value for the gender split is greater than that for the class split, we say that gender is the right variable on which you should make this split. Okay. So this is the second technique that we have, that is the chi-square technique. Third technique that we have is the information gain. So this formula is slightly longer. Okay. Same example, but this is the formula which you use to calculate the information gain. Information gain is equal to 1 minus entropy. Okay. So this entire technique, the most important part is calculating this value of entropy and then taking 1 minus that entropy. Okay. And how do you calculate that entropy? This is the formula that you use: minus p into log p to the base 2 minus q into log q to the base 2. Okay. So p is probability of success and q is probability of failure. Okay. Now, if you just calculate the entropy for the parent node, right? That is parent node as in the entire data set, this 30 students, out of which 15 of them play cricket or 50% play cricket. Okay. So for the entire data set, if you calculate the entropy, it will be 1. Okay. So this one value indicates that it's a very impure split. It does not have any kind of separation because everybody is mixed over here, right? And this is basically the worst possible scenario. Naturally, because you have not made any split, you have not attempted to classify this data into playing cricket or not playing cricket. You just put everyone together. So the entropy here is 1, which means it is an impure node. Okay, and the information gain is 1 minus entropy, right? So 1 minus 1, so information gain will be 0 for the whole data set. But then you do the same procedure. You split based on gender or you split based on class, and then you calculate this entropy value, and then you take 1 minus of that. So how do you calculate this entropy for the gender variable? Again, for each subnodes you have to calculate it, and then you take a weighted average. Okay. So for the female subnode, it will be 2 by 10, right? So 2 is the value of p, 2 by 10 into log 2 by 10 to the base 2. This formula here, p into log p to the base 2, minus q into log q to the base 2. Q is nothing but 8 by 10, that is 10 minus 2, right? That's 0.72. And similarly for this node also you calculate same formula, right? 13 people play cricket, 7 do not play cricket, so this gives you 0.93. Then you take a weighted average, 10 female students and 20 male students out of 30, weighted average is 0.86. Okay. So similarly for the class node, right? 6 people play cricket in class 9, 9 people play cricket in class 10. So 6 out of 14, 8 out of 14 P and Q for class 9, and 9 out of 16 and 7 out of 16 for class 10. So this gives you the weighted average is 0.99, 14 by 30 into class 9 plus 16 by 30 into class 10. Okay. So in this particular case, if you see, information gain is 1 minus 0.86 if you are splitting based on the gender, that is 0.14. If you are splitting based on the class, it is 0.01, that is 1 minus 0.99. Okay. So again, information gain is greater for gender, right? So you will say that splitting based on gender achieves the higher accuracy, so you will go ahead and split based on gender. So these are the 3 techniques that we have for identifying the variable to split or to build the decision tree based on. Okay. The 4th technique, like I said, is something that cannot be used for categorical variables. It's used for continuous variables. I have not covered that today, but this particular thing what we have gone through just now is the most important part of building the decision tree. Okay. So now you have chosen the right variable to split based on and you have built the decision tree. Okay. But for how much long will you, or how big a decision tree will you build, or until when will you build the decision tree? So that's the next question. So that is where we say we have some criteria, or we have some methods to fine tune the decision tree so that it's more accurate. Okay. So these are nothing but, first one is the minimum number of samples for node split. So node split is what we have here, right? So this particular thing is a node, right? So how many samples should this node have in order to make this split? So you can specify. So why we give this is basically in real time when we are working with large data sets, when you go further down the tree, the number of observations or number of samples in each node will decrease. So you could possibly get to a point where a node has only 2 or 3 samples or 2 or 3 observations. Okay. So it doesn't make sense for you to build a decision tree based on those 2 or 3 observations, right? So that is why you specify a minimum number of samples for a node split. Okay. And then minimum number of samples for a terminal node. Okay. So that is nothing but, again, you could get to a point where there is only 1 female and rest of them are males, or 1 male and remaining everyone is female. So that kind of a split will not be very accurate. Okay. So that is one more criteria that you specify, minimum samples for a terminal node. maximum depth of tree is nothing but the number of levels that you have in your decision tree. So here we have only one level, so depth is 1, but there could be situations where you split this bucket further, and there could be many levels in the decision tree, like what we saw here in this first example. So here this is one level, this is the next level, this is the third level. So like this, how deep can you possibly go in your decision tree? So that also you can specify. And then the maximum number of terminal nodes, which is the number of final nodes that you have here, and then the maximum features to be considered for the split. Okay, so features as in, let's say, so here we had only 2 features. So one feature was gender, the other was class, right? So there could be, so typically in large data sets, there could be 100 features or 200 features, right? So out of them, how many features should you actually consider while building this decision tree? You can consider all features, or you can consider those features which you consider to be important. You can do anything, right? So these 5 parameters that we saw here are something that these data science software packages allow you to specify. Okay, so we talked about these 3 techniques, right? Gini coefficient, chi-square, information gain. See, manually it's not, so here the data was very small in size, so we were able to manually calculate each of these 3 metrics and decide what is the best variable to achieve this split. Okay, but in real time, this manual calculation will not be possible, right? So when you have a data set with lakhs and lakhs of rows and hundreds of variables, then it is no longer practical to calculate these metrics for each of those variables. So that is why the statistical software packages such as R or Python already have these parameters built in. So they have already a decision tree library or a set of functions. There you can specify which is the method to use, whether you need to use Gini coefficient or chi-square or information gain. Okay, and they also allow you to specify each of these 5 parameters as well. What is the depth of the tree, what is the minimum number of samples, and so on. Okay, and this particular technique, right, maximum depth of the tree. So this is also what we call as pruning in data science terminology. Okay, it's easier to, or it's better to know these terms so that in the course of conversations when someone else talks about these things, it will help if you are familiar with these with this terminology. Okay, and decision tree is also something what we call as the white box technique. Okay, so typically there are 2 types of techniques: a black box technique and a white box technique. White box is nothing but a transparent technique where we are able to see how the algorithm works in the background. Okay, a black box technique is one where we cannot see how that algorithm works. So here this is a transparent technique because we are able to actually visualize the decision trees and see how the algorithm has arrived at the decision, right? So this is an example of a transparent technique. So yeah, so that's what I had on decision trees for today.